Video, I'm looking at a circuit with resistors and inductors, or one inductor, a DC power supply. I'm just going to call it a battery and oscilloscope. So those items in National Instrument Multisim are found under the ground, and power found under this. The inductor and resistors are found under basic, inductor, resistor. And then the oscilloscope is from over here, and I like the second one. I like the 4-channel. Okay, and I have a switch which was also under basic. And I'm going to flip the simulation on. I'm going to click into the workspace. I'm going to flip the switch by hitting the space bar up and then down, and then I'm going to turn off the simulation. When the switch is up, the battery is part of the circuit, and then we will see an increasing current and therefore an increasing voltage across this resistor. But what an inductor does is sort of like opposes a change. So without the inductor, it would be a fairly immediate rise up, almost the sort of the flipping of the switch, and the resistor would, the voltage across the resistor would rise quite rapidly. This is going to slow it down, and we're going to see a sort of a slower rise over some time. And that's what we'll be interested in, the sort of the time constant for how long that takes. And when we flip the switch down, we're taking the battery out, we're disconnecting the battery, and now we have a circuit here, and we're going to see the current die down from what it was. But again, the inductor doesn't like, opposes changes in current, so it's going to take a while for that current to die down. So we'll see sort of an exponential dying of the current. The voltage across the resistor is proportional to the current. So it's the current will die and the voltage, we'll be looking at voltage because that's what the oscilloscope measures. So in going up, we're looking for this form. We're going to be interested in our simulation of finding what we call the time constant tau. And so if the variable time is equal to 1 time constant, we find out then we are up to, I'm going to call it 63% of the voltage we're going up to, the saturation voltage, which in this case will be the 9. And then when we are coming down, it is 1 time constant is, I'm going to call it 37% of some initial voltage. Now it'll probably get, this takes place rather rapidly, so I will probably be at the full 9 volts. But really this is based on where you start. So it doesn't necessarily have to be the full 9, but that's probably where I'll end up in this case. Okay, so again, I'm going to turn the simulation on. I'm going to click in the workspace, so it'll accept my keyboard, and then I'm going to hit spacebar up, spacebar down, and turn the simulation off. Let me open up the oscilloscope so you can sort of see this happening. All right, so again, I turned this on, I clicked in the spacebar, and turned it off. And you get a lot of flat. And then suddenly I'm up. So now we can play with this time scale. I want to find this up and down more rapidly. I can sort of reduce the time scale. And then when I find, oh, here's where it's rising, then I'll lower the time scale to sort of stretch it out. Stretched out a little bit more. But sometimes if you're too stretched out, it's hard to find where the rise and the fall occur. So, you won't be able to play with this time scale. Okay, that's enough of a change there for me to see what's going on. And I want to get into this, what I'll call the corner here. So I'm down at this small 88 microvolts. So I wasn't quite at 0. And to arrow over and see when it sort of starts to change. And that's, I'm going to call the corner. Okay, there it started to change. I'm going to go back. And then I'm looking to go up to, what did we say, 63% of the saturation, which will be 9. So 9 times 0.63, and we're looking for 567. So I want this second voltage of this, I usually call it a needle, 2 to be 567. I can drag it, and I can also sort of fine tune it with these arrows. I'm just looking for close to 567. And so then it also does the subtraction for me. The 276 is the time between these two times. Okay, and then what does theory expect? Now I have it off, so I'm not running, but I'm going to flip the switch up. And when the circuit is this way, then the inductor L1 is in the circuit and R1 is in the circuit. R2 is not in the circuit, it's just sort of hanging loose. And the time constant is L divided by R. So 470 divided by 1.78. And that is 264. And over here, I got 276. So sort of a reasonable agreement between the theory and the simulation here. Okay, and then the units, I'm dividing millihenries by, and a henry divided by an ohm would be a second. And I've got milli thousandths divided by kilo thousand. So I've got something small divided by something big. So I want something sort of, I don't know, doubly small, if you will. So I'm getting microseconds, 10 to the minus 6. 10 to the minus 3 divided by 10 to the 3 is 10 to the minus 6, or a micro. Okay, now let's scroll over to the other side and do the going down. So I missed it. There we are. Here's the going down. And if I want it, again, I can play with the time. I could stretch it out more if I want. And I'm looking for this. This is the 9. It got all the way to the 9. And I'm looking for that corner. So it's still at 9. And then I'm looking for it to start to change. And then I'll go back. It just started to change. I'll go back. And now when going down, I'm looking for, I'm going to call it 37% of the 9. And that's 333. So I'm looking for this number 2 here to be 333. There. So we're sort of close there. All right. Time constant now is 124 microseconds. Okay. And when which is down, now here's the circuit of interest, and it's L1 is still in the circuit, R1 is in the circuit, but R2 has joined the circuit, and R1 and R2 are in series, so their equivalent resistance is the sum, and the time constant is the L divided by the R. So I'm going to take the L, 470, and I'm going to divide it by, and then I'm going to bring in parentheses and add 1.78 plus 2.2, close the parenthesis, equal. And the theory says 118 microseconds, and what I'm getting simulationally is 124 microseconds. So a pretty good agreement there. So that's what I wanted to show you, this circuit. Here is the sort of math of it. When the battery is connected, the current across the resistor is increasing, and therefore its voltage is increasing. The time constant, it's not the time for it to fully reach its saturation, but to get up to 63%. That's just the sort of math of it. So this parameter here is called tau, the time constant, and it corresponds to when we get to 63%, when we're going up, and it corresponds to 37% when we're going down. And there can be different components in the circuit in going up and going down. So that was also demonstrated here. All right, thank you for your attention.